Okay. Okay. Hey, everyone. Good afternoon and welcome to SE 350. So today we'll go through the introduction and I'm hoping to finish it. So let me time myself. So we're going to go, we're using Teams. So for those of you who haven't used live events, there is Q&A. So when you ask a question, you can just type it there. I'll see the question. Be advised that there is a 20-second difference from when I'm talking until you hear what I'm saying. So sometimes you might post a question and I acknowledge or respond later. So that's because of the delay. I try to answer all the questions. When you ask a question, it comes to the Q&A. I see it, others don't. When I respond, then I publish the question, or I publish the question and then I respond. Okay, that's that. Let's get started. Today, we'll see how things work in SC350. Hopefully we have time to talk about what operating systems are and what makes them or studying them really exciting. Okay, so for those of you who are here, you probably have gone to the website. That's where you got the link. So the course website is posted. I'm going to just quickly walk you through it. Yep. Okay, so a bunch of stuff we're going to talk about. I think the most important piece of this is a schedule. Here it's tentative. Things might change, and I'm actually expecting it to change. But overall, this is going to be the schedule. Pay attention to the event. So there we have the deadlines for the quizzes and for the projects, lab projects. The lectures, the PPTX files and PDF files will be hosted on GitHub. Right now, there is only the introduction. I'm hoping to publish all of the lectures by the end of this week. I mean, probably weekend. Yeah, so there is the reading here, or OSPP stands for the main textbook, which is Operating Systems Principles and Practice, the second edition. There are a bunch of optional reading sometimes. Excuse me. What else? Oh, yeah, this portion, the resources. So this here is actually important. For those of you who want sample examples and sample exams, here is where you can find them. So there's the Berkeley archive with, I don't know, 50, even more so exams. There are also my own exams from winter 19 and winter 20. Winter 20 is when pandemic started, so we only had a midterm. So yeah, you can find those. Definitely, it's a quick read. Try to read the FAQ here. I lay out what the quiz policy is and also what the project policy is. I'll talk about them a little bit more in the lectures. Okay, going back. So Piazza is also up and running. There is also an anonymous feedback form. So whatever you want me to hear, whatever feedback you have, use this. This is anonymous. It will be open during the term. So anything positive you like, anything negative you want to improve, use this form. Just for my own feeling, try to do positive stuff as well. If I just keep negative stuff, I get depressed. So if something is good or something is going well in the course, make sure that you're giving me a thumbs up there, because I mean it's for your own good as well, because maybe somebody else doesn't like it and they tell me, and if I don't have any references, I think that okay, I should change it, not knowing that you actually liked it. So anyhow, that's that. Okay, so online, in person and stuff. For now, at least we're online. Very likely the course will be, the lectures will be online throughout the semester. I have to confirm that. I mean, we'll wait first to see what the university policy is. But even if other courses move to in person, we might stay online. But for now, we're online. Lab tutorials, for now, online. If we move to in person, probably will be in person. And then there's office hours that you can book using the website, although it's yet to be set up. I haven't set it up. So if you go here under my name, you see, I'm gonna, yep, here. So you can book appointments here, as you can see. So again, it's not set up yet. It will be functional soon, where you can click and book an appointment with me or TAs or the lab instructor. For the lab instructor, you can see it under Irene's name. Okay, going back. Okay. I will try to use the, oh, somebody has messaged that I'm doing great. I sort of know, but thank you for saying. Publish. Okay, so I'm going to use some of the tutorial sections for the course because we have a lot to talk about. So I'm going to probably use the tutorial sessions to run some examples. One thing I forgot to mention, if you go to the website, this schedule has the Tuesdays and Thursdays. It also includes Wednesdays, which is our tutorial session. If you see a link there, it means that we have a tutorial that day, and you can use that link. If there is no link there, it means that there won't be any tutorial that day. Another thing, after this session this live event is done, you can use the same link on the website to watch the recording of the lectures. I will try to also upload the videos on YouTube and include the link on the website. But if that takes time, then just use the Teams. So the same link that you just used to bring you to this live event, you can use it to watch the recording of this lecture. Sorry for switching back and forth. Anyhow, okay, moving on. 8 minutes into the lecture, I am Sayed Majid Zahedi. I'm a professor at ECE. I joined 2018. I have taught, this is the third time I think I'm teaching SE350. This term I'm also teaching EC350. There's a little bit of difference between the two courses. EC students have taken EC252 before. So for them, the EC350 has about 25 to 30% more material than SE350. So I'm probably teaching you distributed systems next year. We'll see. That is tentative at this point. Your lab instructor is Irene, and she will be handling everything about the labs. And she has already, I think, reached out to you. Yeah, so she has been doing SC350 for a while. She's very experienced, and definitely make sure that you use her help. Okay. We have 2 TAs this term. Their email and their names are available here in the slides if you want to contact them. Your main textbook is as I said, OSPP, Operating System Principles and Practice. I noticed that looking at the evaluations from the past few terms, students said the book was not helpful. I don't exactly know what they meant. I think what they meant is they never went to the book because everything is based on the slides. But when the evaluation comes, don't say it wasn't helpful if you really didn't go to it, because it's absolutely helpful and good. But I don't think you will need to read the book unless I do a terrible job presenting. But everything will be in the slides. So there are 2 other references, the OSTEP, which we will actually use at least for lab 1. This one is freely available. And then there is the Operating System Concepts, the 10th edition, the library has it. The library actually also has the OSPP book if you're interested. Okay, here in SC350, we will just talk about the key design abstractions that have emerged over time. So we'll see, we start from back not a century ago, but 1940, 1960s, and then we come until now. There is a lecture that I will post at the end of the term that talks about why designing operating systems or rethinking the design of operating system is essential in today's computing paradigm, because the hardware has changed, the software has changed, and we need to rethink the design of operating system. In that lecture, which is a keynote from OSDI 2020 or 2021, I'm not sure. I got the question. I will answer it later. If I don't answer it, you can ask the question again. So in that lecture, you will see that people usually say, okay, we have Linux. Linux is working. It's open source. Everything is fine. Why should I even bother looking at operating systems, looking at designing or implementing them? But that's the wrong perception, because Linux has shown to not work well with today's technology. It works for a specific domain, maybe data center servers, but not for everything. And that's very important to note, so that you don't just shut this door and say, okay, I'm not going to think about designing or implementing operating systems. It's very important. Okay, so why take SC350? Because you have to. But other than that, it's an operating system. The operating systems are everywhere, as we will see. And you might end up designing your own operating system. This course will be perfect for you. You might end up adding parts and components to an already existing operating system. This course will be good for you. At the end of the day, if you're programming, this course is perfect for you. It shows you what's under the hood, what's going on. And then you can use the concepts that you learn in this course everywhere you go during your studies. Okay, now important stuff. Evaluation. There, at least as of now, there is going to be an in-person final worth 30%. Lab projects are going to be 50%, and the quizzes are going to be 20%. There'll be 3 lab projects, and there'll be 9 quizzes. And from the quizzes, we'll just take your highest seven highest grades. Now, quizzes are really designed to take 10 to 15 minutes. These are true-false quizzes. They're online on Learn. They're open book, so you can use all the resources available on the course website, even during the quiz. These are really simple. They're designed to be simple. They're designed to force you to look at the slides. That's it. So don't be scared of them. Once you take quiz 1 and 2, you will probably relax about them. They're just there for me to give you points. That's pretty much what it is. Now, when it comes to grades, I'm kind of famous, kind of. At least there is a Reddit post on what I did winter 20 when the pandemic hit. So I gave the class, at that point, the in-person final, what we announced was 50%. And then once the pandemic hit, we couldn't have the final. So some other courses like CS 350, they had online exam. I said, no, that's unfair. We can't proctor, and it's unfair to give them 50% on that. And if we were to move the weights to the lab project or the quizzes, it would have been, again, unfair, because maybe somebody counted on this quiz or this lab to be 10%. And now if I say it's 20%, 30%, it's unfair to them. So what I did was I gave the entire class the whole point on final exam. So everybody got 100 on their final exam. So I'm saying this to say I really am lenient when it comes to grades. So don't be afraid, don't be scared. You're gonna get a good grade. This course is about learning something that will help you in your career. Okay, going forward. Please read this. So you can consult your textbook. You can use any resources available on the website. You are not allowed to communicate with anybody else, your mom, your dad, your friends, nobody, but the teaching staff. So you can email me or post private posts on Piazza. So these are the 2 ways of communication. So either email me while you're taking the quiz, or post a private post on Piazza. Usually I will try to give you at least 3 or 4 days to take the quiz. The quiz is going to take, as I said, 10 to 15 minutes. And after the quiz, once we release the grades, if you have any questions, you have to use Piazza private posts to ask questions. The reason for this is that different students have different questions, and you asking the question, you're going to reveal a question that somebody else hasn't seen, probably. So that's why you always have to use private messages if you have any question about the grading. Okay, we are in really unpredicted times. Things could happen. As you can see, it was planned to be in-person term. Now we're online. Again, some other things might happen, and we might not have final exam. In that case, if we don't have a final exam, my contingency plan at this point is, let me actually go back, is to move 20% of the final exam to the quizzes. So quizzes become 40%, and move 10% to the labs to make the labs be 60%. So again, if we don't have in-person final, Then we'll have labs weighted at 60 and quizzes weighted at 40. So I'm telling this upfront so that you know what the contingency plan is in case that we don't have a final exam. Okay, labs. We're going to use the Kyle boards to write a real-time executive. You have to form groups. Last time I checked, most of the class has already done that. Be careful, the deadline for that is January 11th. Well, I have to change this. It's actually 8:30. You can split up only once. When you split up, you will lose your sign-up points. So you will see how much sign-up points we're putting. But if you split up, everybody in the group will lose their sign-up points. This means that please pick your teammates wisely to avoid the split-ups. Okay, somebody has asked me about the quizzes. Will the quizzes be timed? Yes. So you have 3 days to take the quiz. The moment you start the quiz, you have about an hour, I think, to complete it. An hour is more than necessary. It's going to take like 10 to 15 minutes. Okay, so these are, again, tentative weights that we're putting on labs. The sign up has 3 points. So if you split, you're going to lose this point. Then the rest of them, there is the 33% and then 32% labs or projects with the deadlines. Again, the deadlines, you can find them on the website as well. What else did I want to say here? Yeah, I think nothing. So everything I say is in a 24-hour format. So 8:30 means 8:30 a.m. If it was 8:30 p.m., it would have been 20:30. Okay. Okay. I have a bunch of things that I'm going to actually move on. So these are really generic suggestions, let's put it that way, for your lab project to work. So according to many, SE350 lab project is probably the most intensive and time-consuming lab they take during their undergrads. So it's a lot of work, but at the same time, many people have said it's very rewarding. Now, to avoid any stress or any last minute, all-nighters, start early, ask questions on Piazza if you have, get help, and finish on time. Did I talk about grace days? Remind me to talk about grace days if I don't have a slide on it. Okay, so somebody is asking about how the 10% that if we don't have a final gets distributed to labs. The distribution of the points won't change. So whatever percentage labs have, 3% of that is for group sign-off, 33% of that is for P1, and so on and so forth. So when we add the 10%, the entire lab becomes 60%. Now you multiply that 60% to all these percentages here. Hopefully I answered that question. Okay. So there are two ways to divide your work: functional or task. Each one of them has their own benefits, their own disadvantages and advantages. Make sure you make this decision in an informed way. So definitely look at these slides. Again, because I want to cover a lot of material today, I'm going to jump. These are really suggestions for your project to go well. Do communicate. The documentation is actually also good. Coordination is good. In the past, I would ask groups to have group managers, somebody who coordinates everybody. And I think that's important to have. So this time it's not forced or reinforced, but try to have one. So pick one of you as a project manager who would coordinate among the group members, and you can actually rotate the project manager role if you want. Give each other a break. So meaning that, mistakes happen. It's inevitable. Don't think about split ups at the beginning. So just because one problem has happened, you don't need to split up the group. To minimize errors, try to document. Now, documentation, code documentation, adding comments, having actually, a whiteboard, kind of an online whiteboard for everybody to put their ideas is also important. Yeah, again, I'm gonna move on. Another thing is test your code constantly. Don't write a big chunk of code and then decide to test it. Believe me, it's not gonna work well. Whatever you write, do a test locally. Chances are that in your group you're going to divide the work between each member, and at some point everybody is going to merge their branches, and you don't really want to start testing at that point, because then you don't exactly know where the problem is coming, if there is any. So test locally, test at each step, test, document. These are really important. Coordinate, communicate. These are, I'm just saying it, and it might look cliche, but definitely there is something to it. It's something that has lasted for this long, and people have stressed it. It means that it's actually helpful and it's actually practical. Okay. I did have a late submission stuff. Okay, so we have 3 grace days that you can use. After that, you will get 15% penalty per day, and you only have 3 days for each project. So P1, you can at most have 3 days, 3 late days. And 10 minutes late is equal to 23 hours late. So we always round up. Please be advised. So don't come and say, oh, it was just 5 minutes, it was just 2 minutes. Anything after the deadline until 24 hours is considered 1 day. And then after 24 hours until 48 hours, that's considered 2 days. After 40 hours to 72 hours, that's 3 days. And after 3 days, we don't accept any submissions. Okay, I got a bunch of questions. Let me finish the administration stuff, and then I answer the questions. Collaboration policies. You can explain concepts to others. You can discuss algorithms and test cases with others. You can help debug somebody else's code. You can help them. you can search for generic algorithms, but you cannot share code or your test cases with any other group. You cannot host your code on GitHub in a public way, even after this term. So even after this term, you cannot share them on GitHub. You cannot copy or read other groups' code for the sake of writing your own code, and you cannot copy or read online code from, let's say, if there are any like from previous years. And we do have a zero tolerance policy. We run MOS, and if we catch any, I mean, just be advised, we have all the submissions from decades of this course being taught. So we run against all of that to catch any plagiarism. If you have questions, you know, contact me or your lab instructor, preferably through Piazza. Try to not send individual emails unless necessary. There's always the private post on Piazza you can use. Once the office hours are in place, you can just take, you know, book appointments if you need to. So your first assignment is to sign up for the groups. Okay, I guess I can now take some questions. I start from the top. How are the labs going to be tested? Is there marmoset or whatever that is, or some sort of automated testing for it? I'm going to leave that to Irene to explain exactly, but yes, we do have automated testing. So we'll have demos once after the deadline. There is a demo session. During the demo, which is about 35 to 40 minutes, you will present your code to a lab teaching staff, and they run your code against our test cases. If you pass all of them, good for you, you get 100. If there are problems, if you don't pass those tests, you will have a chance to figure it out during the demo. That's all you have. So during the demo, if you can figure out what the problem is and you can resolve it, again, good for you. No penalty, you can fix it, and then you get the points. But whatever happens in that 35 to 40 minutes is it. So you won't get another chance to demo your code. So, and more details about demos and how you book them and all of that will come later. Another thing, which I probably forgot, I now don't remember if I mentioned it, you can pick teammates from other lab sections. Just be sure that there's a time that works for everybody, okay? Will there be any practice quizzes? I don't know if you missed the first part of the lecture, but on the course website, there is this part, resources. So here, as you can see, resources. So here I have posted ton of examples. So ton of, you know, samples you can definitely use. Will documentation be part of the lab's grading? In some labs, yes. Everything that is required for you to submit will be clearly stated in the lab manual, which will be available to you on GitHub. Again, Irene will post a video soon talking about all of this. Love the memes. Thank you. I love them too. Okay, how are the labs going to be tested? Oh, okay. I think somebody, okay, they re-asked the question. Okay, I think I answered it. I think I answered the documentation. Is it 3 days per project or 3 days for all projects combined? So you have 3 grace days for all projects combined, but per project you have 3 days. You can't have more than 3 late days per project. Now, you know, you will count the grace days that you've used. After that, you will get penalized by 50% per day. What difficulties do you anticipate for groups with members across different lab sections? Do you advise people in these situations to try to switch into a common lab section, or do you think it'll be fine? It usually is fine. Just make sure that there is at least one lab section that works for everyone, because that's where you're going to do demo. So the demoing is the important part, that you want everybody to be able to be there when you're demoing. So make sure that at least one of the lab sections work for everyone. Okay, so I answered all the questions. How much time do we have left? Is there any way to make my phone not go dark when the timer is running? That's so stupid. I mean, I'm running the timer, it should just stay up. Why does it? Yeah, Mac OS. Not good. Okay. I think we have another 40 minutes into. Yeah, we have time, hopefully, to finish the introduction. Okay, so overall message: work hard and relax harder. These are stressful times. I mean, now less so than before, but still, try to find time for yourself to relax. Don't get lost into the coursework. Okay, what is an operating system? So in one word, what is the text on your mug? Okay, my wife bought this. That's my honor. So yeah. Proudly. Thank you for asking. Okay. Okay. So again, I'm not going to answer questions until I'm done with at least a part of the lecture. So what is the definition of an operating system? This is kind of not controversial, but there is no universally accepted definition. But if you really force me, then I would say it's kind of like what is shipped to you when you download an operating system. Whatever comes with that original package is kind of operating system. Take it or leave it. But it's really not a good thing to do, to try to define operating system. Instead, the right question to ask is, what does operating system do? So then anything that does that becomes operating system. So we're going to define operating system as its functionality. What does operating system do? And that becomes basically a definition that you can use for operating systems. In essence, very high level, the operating system is going to give you an abstraction layer. Thank you for the comment. So the operating system is going to give you an abstraction that abstracts away the hardware for the software. So that's very high level. On top of that, operating system is going to provide protection across resources. Protection is always good, and sometimes necessary. So on top of that, operating system has duty to provide security and authentication. And if you put protection and security, you want to protect all these resources from accessing access from unauthorized accesses. That might restrict you to an extent where communication is not possible. So that's another thing that the operating system has to do, which kind of makes it really difficult. You have to isolate and protect, but also allow communication between, let's say, different processes, which we'll talk about in more details in the future slides, in the future lectures. Now, I'm going to just categorize what the operating system does. And again, remember, we're going to define operating system by its functionality. So I'm going to categorize it into 3 categories. The first one is the illusionist functionality of operating system. It has to provide this abstraction layer of the physical resources that are available in your computer to the applications. For example, when you write an application, you usually don't worry about how much physical memory you have. I mean, there are cases where you do care about that for performance reasons, but usually when you're writing your program, you're not really thinking about how much memory you have. You kind of think that you have infinite amount of memory available to you. Or you don't even think about what other application is running alongside my application. When you're submitting your VMs, for example, to the cloud, you really don't care about what other VMs are going to run, unless you're a malicious user and you want to hack them. But you usually don't think about that, right? So let's dive a little bit into that. So we have this hardware. I have a big box, so you should expect things to go in that box. And then we have the software. And inside, the most important parts that we're going to consider in this course is basically the processor and the memory. Now you could, very high level imagine that in the memory, I have a portion of memory that is, designated to the memory that the operating system itself needs, and then a bunch of other memory regions that, we want the operating system to provide protection for. So we want some access control to different regions of memory. For example, you don't really want a process to come and access the memory that is owned by the operating system. That would be really bad, right? Because whatever operating system is doing, you want to keep it for just operating system. If other processes can come and access that, then that's bad. And unfortunately, it actually happens on all of our computers because of a hardware bug, which we will talk about later in the course, called the meltdown. The meltdown bug that was discovered a few years ago, and there's meltdown, there are some fixes, but then a Spectre happened, which there is no solution for it. But anyhow, I'm so sorry for throwing these jargons into your face. But anyhow, so we want operating system to not allow people access different applications to access different applications memory regions. Now, the processor has a bunch of registers inside. We want to be able to, when we're running a certain process, to bring its data to these registers. So that's what happens. And to speed this up, we probably want to use cache, which again we will talk about. These are basically the overview. This is an overview of the topics that we're going to talk in details in this course. And then to speed up even further, we have to have other caches like page table caches, which is called the address translation caches, which is called the TLBs. Apart from the processor and the memory, there is the storage where you have your permanent data residing. You also have other I/O devices like your Wi-Fi, your display, your GPU, your keyboard, your microphone, whatever. So these are also hardware that is available to us. Now, there is a control that is going on that connects all these pieces together. And we want this whole box, hardware box, to be protected from the software. We don't want to allow software to arbitrarily access hardware. There is an ISA, which is kind of the interface between hardware and software. It says, you know, this is the instruction set that you can use to access the hardware. But on top of this, we want to put the operating system to protect, to protect these hardware resources from the processes. Now, to do so, we're going to create abstractions. For example, for the processor, we will create the abstraction of threads. This is the part 1 of the course. Then for the memory, we're going to create this abstraction of virtual address space, which is going to be the second part of the course. And then for the storage, we're going to create the file systems. That's an abstraction for the storage. Again, the third part of the course. Unfortunately, we don't have time to talk about sockets, but sockets are the abstractions that the operating system provides to the processes to access network devices. So an abstraction that we're going to use is, and we'll dive into it, we'll explain it, we will define it in details, is the process. So this concept of process is the abstraction that the operating system provides. And you know, the process becomes the running instance of your program. So you have your program, you start executing it, it becomes a process. Now this process, through operating system, can access hardware resources in a protected way. Now, on top of all of these abstractions, sometimes operating systems also provide system libraries. This is like, for instance, printf. So when you want to print something on the display is a hardware and it's protected. Now, to allow different applications to use hardware easily, operating systems also provide system libraries. Some people include system libraries in the definition of operating systems. They say, see, this is doing the functionality that we need an operating system to do. Therefore, it's part of the operating system. So we talked about that one. The second functionality or job of the operating system is to act as a referee. This is basically that we want the operating system to come in and decide who gets access to what. Now let's look at this example. So going back to what we had, we're going to put this operating system to protect our hardware. On top of it, we have the process abstraction. Now let's say we have two processes running. I have left 23 minutes. Gosh, I'm so bad. So the course and the class ends at 50. So I have 30 minutes. That's good. Okay. Sorry for that. We were talking about the referee job of the operating system. Now let's say I have two processes running. I want them to be isolated, and let's say I have only one processor. Now I can't run both of the processes at the same time on my processor. So what I'm going to do is that the operating system is going to kick in, decide, okay, at this point, I want to run the first process. So I will bring the data I need for this process to the processor, to the registers, and I start doing and executing this process. Now, if time comes up and I want to context switch, then I want to bring the data from the other process to the processor for the execution. Now, right here, I talked about scheduling, which is another topic that we will talk about, which is who gets to use the processor. So this is job of the operating system as a referee to schedule processes on the processor. Now, another thing here is the protection. If process 2 wants to access process 1's data in memory, this should be a no-no. Or if process 2 wants to access the operating system's data in the memory, that also should be a no-no. So if process 2 wants to, in an arbitrary way, access the storage, that should be also a no-no. The same with the network. So all of them, we're going to say no. You're not allowed to access this, for example, memory. It's going to come as a page segmentation fault. You didn't have, right access. Correct access to read or write from these files. Now, usually where we draw the line, where we want to protect stuff, is here. This line that you see here is the line that we draw. The reason is we usually want the processes to run on the processor. So it's kind of like if we, limit the access to the processor, it's going to cost us time and performance. Although I have to say, even though we give the access to the processor, we give kind of like a unprotected access, there is still some protected access. For example, as we will talk about in the future, there are some instructions that we don't want the user process to execute. So we still have some instructions that we don't want to allow a user process to execute on the processor. The same with memory. So again, for performance, we want them to really be able to use the memory. Although we provide an abstraction to it, which is the virtual memory abstraction, which again, we will talk about. But anything other than that, we really want to aggressively protect. Okay, so we talked about illusionist operating system acting as an illusionist. We talked about operating system acting as a referee. We're going to talk about operating system acting as a glue. So I got a question. Oh, somebody's asking about what exactly this red line is signifying. Let me publish this. So really what this line is saying is, other than processor and the memory, which the operating system kind of gives direct access to, right? When your code is executing, the operating system is not going to kick in for every instruction that your code executes. So if your code is executing add and then a divide and then an if, operating system is not going to kick in every instruction and check it and see what's going on, right? So kind of operating system is giving you access to process. The same with memory. If you read something from memory or write something from memory, the operating system is not going to kick in directly in each one of those. So it's kind of like operating system gives you some access, some direct access to those resources. However, if you want to write data to your storage, or if you want to use the network card, or if you want the display, this is where the operating system comes in and says, oh no, I have to check it. So that's where you use these system calls. So you say, open this file for me. So this is like a system call. You tell the operating system, open this file for me. And then operating system does it for you. So you don't have a direct access. You have access through operating system calls, which again, we will talk about in more details. Hopefully I answered that question. So kind of anything above this line, we're giving them sort of direct control. Anything below this line, we're putting a lot of indirection in the loop. So we're, asking everybody to go through the operating system. I have to say, I was kind of like not sure if I have to say it here or not. It's kind of like an advanced operating system topic, but the new trend in operating systems design is to also provide some direct access to these devices. And that's for performance reasons. So right now, for example, for those of you who know RDMA, for example, or some networked NVMe stuff, so on-wire NVMe, we're actually allowing the software and the processes to access a storage and network card kind of directly. And that is because of performance. So this paradigm is kind of like changing, and we're kind of in the, it's becoming mainstream. But I don't know if we will have time to talk about those. But generally speaking, we want to restrict access to storage, basically everything else other than the processor and memory. Even processor and memory will provide a lot of protection, which we will talk about. Okay, got another question. So somebody's asking, if the operating system doesn't jump in all the time, how does it check for invalid access to some memory areas, like segmentation fault? That's a great question, and it's a topic of concern for the operating system course for SC350, and we will actually talk about it in 2-3 lectures, I think in the second half of the course. But to just give you an idea, operating system before running a process sets some flags in the hardware, and then delegates the checking to hardware to provide performance. So now when your code is running, if it wants to access something that is not supposed to touch, then the hardware says, uh-oh, something bad happened. And at that time, hardware goes and wakes up operating system and says, oh, somebody accessed something that you told me nobody should. Now what should I do? And then the operating system decides what to do. Again, we'll talk about it in more details. That was a good question, by the way. Okay. Now, the last part is the glue. I kind of alluded to it before. That's basically where the system libraries come in, where kind of operating system acts as a glue to create a unified service to the entire to all the processes. So this is basically the system libraries, the system calls. These are the services that the operating system provides to the processes to use the hardware in a unified way, if that makes sense. For example, as I said, the printf example, or the open function that you use, or read, or write, or sockets. These are the system libraries. These are the functionalities that the operating system provides to kind of unify whatever is in the hardware for the software, again, in a unified way. So that's where the glue part of the operating system comes in. It kind of like unifies the abstraction layer for all of the processes. So like this is another example, for example, the windowing system. When you open a window, or when you maximize a window, you minimize the window, you close a window. So you don't really want each application to go and write the code for using the display, right? That's where the operating system comes in with a system library. It provides the windowing system. Or for example, for your battery, you don't want each application to manage how much energy it's consuming. You allow the operating system to provide one set of functionalities for the entire system to manage the battery. So these are basically the functionality of the operating system that is to make a unified vision and unified abstraction of the operating system, of the hardware to the applications. And usually it's done through the system libraries. Okay, so I'm going to catch my breath. There seems to be no questions, so we continue. The bottom line is that operating system is there to run applications. So we really don't want the operating system to consume most of the resources for itself. We want operating system to be kind of like incidental, not being the bold part that consumes all the resources, but to be the lightweight component of the system that provides access to all the resources to applications. So it's with minimal footprint. As I just in the answer I provided for the memory access, usually operating systems rely on hardware to provide this abstraction. So most of these jobs that we'll discuss rely on hardware. That's why usually you have different operating systems for different architectures. So because what the hardware provides is different. Like what x86 provides might be different from what ARM provides, might be different from what the IBM Power provides, might be different from what RISC-V provides. And the operating system usually relies on those supports to provide this abstraction. But as you will see, I will make sure that I make this point very clear. Usually it's the case that operating system doesn't necessarily need that help, meaning that the operating system might be able to actually do that by itself. The reason it relies on hardware is usually to get higher performance. So usually that's the rule of thumb, that operating system kind of delegates its job to hardware or relies on hardware support to improve performance. And again, I will make sure to make this point clear when it comes. So like when we talk about address translation, I will pause and say, okay, guys, we can do this without hardware, but see if we do it by ourselves in operating system and in software, it's going to take forever to run a code. That's why we kind of rely on hardware to do the job for us. And as I mentioned at the beginning of this lecture, hardware support and operating system continue to co-evolve. And I think we are in a very kind of important intersection of time where there is a surge in new hardware design. There are so many different new designs coming out every day. But unfortunately, when it comes to operating systems, we don't have many options. Usually people go to Linux or Unix kind of systems, or hopefully nobody thinks about Apple, Mac, and Windows, but anyhow, those as well. But I think we're in the times where designing new operating systems, rethinking about the designs is really important. And I will make sure to post the lecture on this last piece to kind of motivate you to maybe, if you're interested in doing research in this area, it's really an important area. The fact that you're taking it at third year doesn't make it less important than elective courses that you're going to take in fourth year. It's really important. Okay, so to just kind of summarize what we've said. In essence, operating systems, what do? They run applications, provide an abstraction, and that abstraction has different parts. For example, file system, threads, virtual memory, and so on and so forth, like sockets and all of that. They manage hardware for us, like they manage memory, they manage CPU, they manage the storage, they manage networking, they manage our battery, they manage every single hardware that we have. And they do this by different algorithms and different data structures. So usually when we talk about allocating CPU, we're talking about scheduling. When we're talking about efficiently using the CPU, we're talking about concurrency and how the operating system provides that. So on and so forth, like providing security and authentication and privacy and all of that. It's really the job of the operating system, using different algorithms and different mechanisms and methods. Yeah, I kind of talked about this. Now, let me see, where am I? How many slides do I have left? Oh, quite few. Okay, so it's kind of unfortunately, the only time in this course that I'm going to talk about virtual machines, because unfortunately we don't have time enough to dive into virtual machines. But this is an important aspect that has to be talked about. So what is a virtual machine? You might ask. So the virtual machine is kind of a software that emulates the physical machine, the physical hardware. So it's a software, but it acts like hardware. So it basically gives the software that is running on top of it the illusion that it's running on a bare metal hardware, and provides, whatever the interface it wants to support. It provides that interface regardless of the actual hardware that it itself is running on. So you could run a virtual machine on an x86, but provide, RISC-V, for example, ISA to the software that runs on top of you. So there are three types of virtual machines. There is the process virtual machine. Sorry, there are two types. There is the process virtual machine, and there is the system virtual machine. Now, let's start with the process virtual machine. This is the easiest one. So the process virtual machine is basically does only one thing, and it runs processes. So I think this figure shows it very well. So I have the hardware, and the hardware provides an actual ISA. Now, the operating system runs on top of that and provides this ABA, so abstraction binary interface. Now, we run our process virtual machine that could potentially use the host operating system, could use the hardware, but then this virtual machine provides a potentially different virtual ABI and virtual ISA to the processes that are running on top of it. An example would be Java, right? So the Java virtual machine runs Java processes, and it's kind of independent of the machine that is running it. So if you run your Java code on x86, you can run your Java code on x86. You can run your Java code on ARM. You can run your Java code on, let's say, RISC-V or whatever. The virtual machine provides the abstraction that you're running on a Java virtual machine. You don't care about the underlying hardware, really. So that's basically what the process virtual machine does. Another example is .NET Framework. Now, moving on from that, there comes the system virtual machine. Now, system virtual machine basically provides an abstraction for an operating system to run on top of it. So with the process virtual machine, what we were running on top of the virtual machine was processes. On system virtual machine, what we're running on top of the virtual machine is operating system. Now, usually in this one, we need a third party to come and help us, and that is called hypervisor. So hypervisor is the entity that manages virtual machines. So I guess I don't have it, but oh, I do have it. So hypervisor creates and runs virtual machines, basically manages them. Meaning that it says who runs now, what is the state of the virtual machine, is it running, is it halted, is it terminated, where does it live, what resources it can, no, actually the resources I take back, basically managing them, scheduling them and such. No, I take the scheduling back as well. Keeping the states of the virtual machines, knowing what they need, what they are, what the state they are at. So that's what they do. Now, there are two types of hypervisor, type 1 hypervisor and type 2 hypervisor. Let's first look at the type 1 hypervisor. So in type 1 hypervisor, the hypervisor comes right on top of the hardware. And it not only manages the virtual machines, but also allocates hardware to them. Basically says who gets the CPU, who and how virtual machines access memory, how they use the device drivers. All of that is done by the hypervisor. Now in type 2 hypervisor, the hypervisor relies on the operating system to do the hardware allocation. So it only manages the virtual machines, but relies on the operating system to allocate hardware. So that's basically type 2. And examples of type 1 is the Zen, the VMware ESXi, and then examples of type 2 are VirtualBox, VMware Workstation, and KVM. Although this KVM is kind of like controversial, some people say type 1, type 2, but based on the definition I just said, it's kind of type 2 because it relies on the Linux kernel to do the hardware management. Okay. Now, there is this new trend that you probably have heard, and it's called containers. So what are they? So containers provide OS virtualization. Compare them to virtual machines. Virtual machines provide full machine virtualization. So basically they emulate the hardware. Containers don't emulate the hardware. They kind of virtualize. So basically, virtual machines virtualize the hardware. Containers virtualize operating systems. What does that mean? It means that, you know, each container has the illusion of running on an isolated operating system, whereas VMs have the, you know, illusion of running on an isolated machine. They think, you know, if you have a VM on Amazon cluster, it thinks that it has access to the bare metal hardware. It doesn't know what other VMs are running there, right? It thinks that I have this dedicated server for myself that I'm using, this dedicated hardware. Now, with containers, that's not the case. So we just think within the container that we have this isolated operating system for ourselves. There are no other processes, for example, running on this operating system. I'm the only one inside this operating system. So that's the difference between VM and containers, and that actually provides a lot of performance benefits because you're not emulating the hardware. So you can actually rely on the operating system to run your application on bare metal. So usually containers rely on the host operating system to provide functionality for them. So that's usually, in Linux, it's going to use the C groups and namespace, for example. Now, if you want to run a Linux container in Windows, that's not possible unless you run first a VM. So you first run a VM, virtual machine, to pretend that you have a Linux machine inside Windows, and then you can run your Linux container inside your virtual machine. But if you don't want to do this and you have a Windows container, you can just run it on bare metal. So depending on your situation, you can run your containers in a virtual machine or you can run them on bare metal. There are two types of containers. There is the operating system containers and there is the application container. The operating system container expects to run bunch of applications within the container, whereas the application container only runs one application or only expect one application. So examples for OS containers is LXC, OpenVZ, and FreeBSD-jail. And the examples for application containers is Docker and RKT. Okay, now how much time do I have left? Only a few minutes, 2 minutes. Okay, I'm gonna see what I can do. So why operating systems are challenging and interesting? This is what happened during this figure shows what what happened in every minute of 2021. As you can see, there was 167 million TikTok videos watched, 5.7 million Google search was conducted. What else? What is interesting? 856 Zoom streaming happened every minute in 2021. And so on and so forth. So it's actually interesting. Now, if you dig, operating system is at the heart of all of this. So all of these systems, the entire cloud and data center technology depends on operating system, virtual machines, containers. And if there was no operating system, none of this would have been possible. So that should be enough of motivation for you guys to pay attention to operating system course. But really, the challenge is how to keep up with evolving hardware and how to tame the complexity of software and hardware and manage them. Okay, so I'm going to stop here. It's 3:50. Thank you for those of you who attended the talk online, and thank you for those. Thank you for those of you who are going to watch. God damn it. Okay, anyhow, thank you for those of you who are going to watch the lecture later. We'll see you guys on Tuesday. Take care, be safe, and talk to you later. Bye-bye.